So if we're going to use the k-means algorithm, how do we actually choose k, the number of clusters that we want? It's a tough question, and one that we kind of have to play around with at the edges before we can kind of converge on a solution. So let me just point out the ones that we shouldn't use, or the problems that we could run into. If k is too small, like imagine the weirdest one, like k equals 1. If we have k equals 1, in this case, there's only one big cluster, and we haven't actually clustered anything. We've somehow ignored all differences in the data set, even the meaningful ones, and settled on just one cluster. And then we haven't done anything. The data had one cluster to begin with. It's called the data. So k equals 1 is clearly nonsensical. But on the other side, we have a clearly nonsensical option as well, which is that every single data point is its own cluster. So if you have n data points in your data set, you have n clusters. And this is obviously silly, right? So we have two nonsensical ends to this particular kind of spectrum. And so the answer that we want has to lie somewhere in the middle. But the question is, how do we actually find that sweet spot? What does that mean? And obviously, as you can imagine, there's a lot of different ways to do this. And it depends on your particular way of defining cluster goodness. And there are several different ways. So we're going to talk about one here, but there are others. And we'll talk about those. I'll at least mention their names so you can look them up if you're interested. So imagine we have a cluster I. So this is cluster 1, cluster 2, cluster 3, all the way up to cluster k. We can compute the distance between the sum of the distances, or the average, however you want to do it, between the cluster center and each one of the data points in that cluster. So we go to each data point in the cluster and we calculate the distance between that data point and the center of the cluster. This is a lot like the variance of the cluster. So this distance here is basically measuring how diffuse the cluster is. If this quantity Si is large, this means the cluster is very diffuse. On average, the data points lie quite far from the center of the data cloud. If this Si is small, this means the cluster is tightly packed, in the sense that if Si is small, then that's saying on average, each data point lies quite close to the cluster center. As we increase k, you can mentally convince yourself that this Si number should go down. That's because, like for instance, in the limit here, if every data point is its own cluster, then the Si is 0 because there's only one data point in the cluster. So the distance between the data point and the center of the cluster is 0 because the data point is the center of the cluster. And so at the end of the day, the sum of the SIs has to be 0. Like we don't have any variability in the data set at all. If k is really, really small, if we have k equals 1, for instance, then basically this thing is the variance of the data set, and we get some kind of decrease as we increase the number of clusters. As you increase the number of clusters, like you're allowing data points to be closer to the center because there are more centers to be close to. So yeah, there should be decreasing SI, but there's probably diminishing returns. So if we plotted this thing, this is what we would see. So in this particular case, we have, or in this figure family, we have on the horizontal axis here the number of clusters, and then on the vertical axis we have the average of all the SIs. And so this is like on average how far is a data point from its cluster center. And what we see here is that it starts quite high when we have just one cluster. It becomes quite small when we have many, many clusters. This is exactly what we decided. But notice the difference here. As we go from 1 to 2 clusters, there's a drastic drop in this average SI and the kind of how diffuse the clusters are. If I go from 1 cluster to 2 clusters, the clusters become much more tightly packed in the 2 cluster case than they were in the 1 cluster case. Similarly, if I go from 2 to 3, there's a pretty large compactification. The clusters become much more compact pretty quickly. And then as we go a little bit further, notice that this drop is not as big. It's not nearly as big. And that's kind of to be expected. There's just kind of diminishing returns at some point. So what we're looking for here is this elbow. So this elbow here is the point at which, like if we were to flip this curve around, you would probably recognize it from like as a productivity curve. Like we want to look for the point of diminishing returns. That's where the function switches concavity, if we're familiar with the calculus version of this. But basically where these jumps go from being really big to much smaller. And we'll talk about kind of the idea or the caveats here. But in this case, it's something like 3. So let's just jump into the caveats. So a few warnings about this. It can be tough to identify the elbow. In practice, these curves are not nearly as smooth as the one that I draw. Sometimes, or drew, sometimes there's some jumping around. And because of that jumping around, it may look like, you know, there are a couple different values that could be the elbow, and that's okay. There are tons of other ways to compete other than average SI to talk about what a good cluster means. The most popular alternative is the silhouette measure, and so silhouette measure takes into account both how far apart clusters are and how densely packed they are. So the basic idea behind silhouette is it doesn't make sense to say that two clusters are good, two tightly packed clusters are good if they are right on top of each other. That's not good because you haven't split out those data points. You know, what you want is two tightly packed clusters that are well separated, and silhouette measure accounts for that, but you can imagine it's more mathematically complicated than the version we talked about because it's kind of measuring a more nuanced thing. So the big idea here is that we're looking for the elbow. So when we look at an elbow chart here, we want somewhere around here. So anything, I would pick 3 here, but I think you could make a case for 2, 3, or 4. 1 certainly not, and 5 certainly not. So I try to like look at the general range of things I think might be acceptable and pick the one towards the middle. But again, we're looking for the point of diminishing returns where these drops go from being quite large to much, much smaller. It could be hard, but this is just meant to give us a place to start in investigating these clusters. Ultimately, we have to try some values of k and see whether we can interpret these clusters and kind of operationalize them. Like once we use this value of k, can we tell a story to ourselves about who these clusters represent? And we'll do that in a future video.